Section 1 Introduction. Let's dive into the world of image segmentation, a complex problem with solutions that can be found at different levels of detail. Imagine you're an end user who wants to segment images. You'd want a simple and effective way to guide the segmentation process, deciding what to segment and how detailed you want it to be across a range of images. You'd do this by providing one or a few examples for the system to use as a reference during training. You wouldn't want to have to gather a large dataset of images annotated with ground truth segmentations, train a large segmentation model, or encode complex properties of target objects. This example-driven approach would give you the power to define and refine the target segmentations according to your specific needs. For example, if you're working on expression recognition or facial alignment, you might only need to segment images of faces into basic regions like the nose, eyes, and hair. But if you're working on visual effects, you'd need more detailed segments like eye bags, forehead, chin, and lips for tasks like wrinkle removal. This is why we need a flexible and customizable segmentation technique that can adapt to different levels of detail. But it's not practical to have a large set of ground truth annotations for all possible levels of detail, which is why one-shot or few-shot learning is so important. Recent research has made strides in few-shot learning, with promising methods like Regan, which uses a generative adversarial network, GAN, to generate data for manual annotation and model training. Another method, SegDDPM, extracts features from a pre-trained diffusion model and trains multiple multilayer perceptrons, MLPs, for segmentation using few labels. Both of these methods excel in segmentation with 10 to 50 examples but struggle with extremely limited samples. SegGPT, on the other hand, uses one-shot learning, training on color randomized segmentation data that includes both instance and part-level details. But while SegGPT is effective, it requires a significant amount of annotated segmentation data for pre-training, which doesn't solve the challenge of training effectively with a single annotation. In this work, we propose a new method called SegmentLikeMe, SLiMe, which can segment any object or part from the same category based on a given template with any level of detail in a one-shot manner. This eliminates the need for extensive annotated segmentation data. We achieve this by harnessing the power of existing large-scale pre-trained vision, language models, such as Stable Diffusion, SD. Recent studies have shown that the cross-attention maps of models like SD highlight different regions of the image when the corresponding text changes. This property has been used to modify generated images and achieve image correspondence. We've made two key observations. First, standalone cross-attention maps can be inherently noisy, leading to imprecise segmentation. To fix this, we propose a novel weighted accumulated self-attention map. This attention map incorporates crucial semantic boundary information and uses high-resolution self-attention maps, ensuring enhanced segmentation accuracy. Second, the text embeddings in SD can be fine-tuned to capture semantic details, like segmented regions, where each embedding corresponds to a distinct segmented region, guided by a reference image in its segmentation map. Based on these insights, SLiMe uses a single training image and its associated segmentation map to fine-tune the text embeddings of SD through attention maps. These refined embeddings emphasize segmented regions within the attention maps, which can be converted to a segmentation map. Once learned, these embeddings can be used to segment multiple real-world images during inference, mirroring the granularity of the segmented region from the training image. Through various experiments, we demonstrate the effectiveness of our approach. Our method, even when reliant on just one or a handful of examples, proves to be comparable to supervised counterparts demanding extensive training. Furthermore, when compared to few-shot methods, our results demonstrate a significant performance advantage. In a 10-sample scenario, we surpass Regan by approximately 8%, and in a one-sample context, we exceed SegGPT by around 7%. In a 20-sample setting, SLiMe also outperforms SegDDPM in terms of mean intersection over union, MIOU. These accomplishments firmly establish our method as a leading contender in the state-of-the-art landscape. Now, let's talk about related work. In computer vision, semantic segmentation, where a class label is assigned to each pixel in an image, is an important task with several applications such as scene parsing, autonomous systems, medical imaging, image editing, environmental monitoring, and video analysis. A more detailed version of semantic segmentation is semantic part segmentation, which aims to delineate individual components of objects rather than segmenting the entirety of the objects. Despite significant advancements in this domain, a major challenge remains the substantial need for annotated data, a resource that is often difficult to procure. One approach to reduce the need for annotated data is to frame the problem within the few-shot part segmentation framework. A recent paper, Regan, proposed a few-shot method for part segmentation. However, this method requires a substantial amount of images from the relevant category. In contrast, we leverage pre-trained diffusion models that are trained on large general datasets, eliminating the need to curate category-specific datasets. Diffusion models are a class of generative models that have recently gained significant attention because of their extraordinary ability to generate high-quality samples. SegDDPM has explored the effectiveness of unconditional diffusion models for the semantic part segmentation task. Compared to SegDDPM, our approach utilizes a text-conditioned diffusion model as a first step. Furthermore, unlike their method, we employ diffusion models with weights acquired through training on general data rather than class-specific data. Additionally, we leverage cross-attention maps instead of relying on internal features of diffusion models, as these maps contain richer semantic information. Moreover, our method demonstrates the capability to work effectively with a reduced number of samples, as few as one, whereas they do not mention the suitability of their method for single-sample scenarios. A popular and publicly available example of conditional diffusion models is Stable Diffusion, SD, that can be used for generating detailed images, inpainting, outpainting, and editing images guided by a text prompt. In addition to these, a large body of work fine-tune SD or use its cross-attention modules to perform interesting tasks. For instance, one study fine-tunes SD's text embeddings to add a new object or style to its image generation space. In another example, researchers use SD's cross-attention modules to impose more control over the generation process. Moreover, in a third instance, authors edit a real image using SD's cross-attention modules. Lastly, a recent paper uses self- and cross-attention modules of SD for object-level shape variation. They propose self-segmentation and use it to apply the variation in only the desired regions. Self-segmentation is a technique for segmenting a generated image by SD in its generation process by clustering the pixels in self-attention map and labeling the clusters with cross-attention map. Different from self-segmentation, instead of clustering, we use cross-attention map to calculate the weighted sum of pixels in self-attention map to get the segmentation mask of each region. This gives our method the freedom to do segmentation at different levels of detail as needed. Although these papers explore the applicability of SD in different tasks, using it in semantic part segmentation is not fully explored. In this work, we take advantage of SD's self- and cross-attention modules and fine-tuning its text embeddings to perform semantic part segmentation using as few as one annotated image. Section Summary. We propose a method called SLiMe that can segment objects or parts of objects with arbitrary levels of granularity using just one annotated image as a reference. We leverage the knowledge embedded in pre-trained vision, language models like Stable Diffusion, SD, to fine-tune text embeddings and generate accurate segmentation maps. Our approach outperforms other few-shot methods and achieves comparable results to supervised methods, making it a leading contender in the field. Section 3 Background. Let's delve into the background of our study. We'll start by discussing latent diffusion models, LDMs. LDMs are a type of generative model that can efficiently compress random input data into a more manageable form, known as the latent space. This is achieved using an autoencoder, which is a type of artificial neural network trained on a large set of images. The autoencoder consists of two main parts, an encoder and a decoder. The encoder's job is to create a compressed representation of an image, while the decoder's role is to reconstruct the original image from this compressed form. The autoencoder can be designed as either a discrete or a continuous generative model, and its performance is optimized using a measure called KL divergence loss. The LDM also uses a diffusion model, DM, to understand the distribution of the compressed image representations created by the autoencoder. One of the great things about a DM is that it can be adapted to represent conditional distributions, which are distributions that depend on certain conditions, such as text or category. In our study, we're particularly interested in LDMs that are conditioned on text. In a text-conditioned LDM, we start with a natural language prompt, which we then break down into individual tokens. These tokens are then transformed into a text embedding using a text encoder. This text embedding is then used as one of the inputs for the DM. To train a text-conditioned LDM, we add noise that changes over time to the image embedding, and then adjust the parameters of the text encoder and the DM to enable the model to predict and remove this noise. In our work, we use a specific type of text-conditioned LDM called SD for two main reasons. Firstly, SD's cross-attention modules create strong semantic connections between text and image embeddings. Secondly, SD's autoencoder can transform an input image into a meaningful latent vector that contains both global and local information, which enhances the relationship between text and image. Next, let's talk about attention modules. The DM used in SD uses a structure called UNet, which includes ResNet blocks and two types of attention modules, self-attention and cross-attention. The self-attention module calculates attention within the image embedding, capturing relationships between different elements within the same image. The cross-attention module, on the other hand, calculates relationships between the latent representations of two different types of data, such as text and image. An attention module consists of three parts: queries, keys, and values. It works by transforming an input query into an output using a key-value pair. In the self-attention module, all the queries, keys, and values come from the image embedding. In the cross-attention module, the query comes from the image's latent representation, and the keys and values come from the text embedding. In our study, we extract normalized attention maps, which are applicable to both the self-attention and cross-attention modules. In the self-attention module, each pixel in the input is associated with an activation map, which identifies pixels that share a similar context. The intensity of this activation map decreases as we move away from the pixel. For example, if we select a pixel on a bird's beak and look at its corresponding activation map, we'll see that it highlights other pixels on the bird's beak and ignores unrelated pixels. The brightness of the highlighted pixels increases as they get closer to the selected pixel. In the cross-attention module, each input text token generates an attention map that highlights pixels in the image embedding that align with the token semantics. For example, if we ask the model to generate an image of a bear and look at the attention map associated with the token bear, we'll see that the pixels corresponding to the bear in the generated image are emphasized. Section summary. Latent diffusion models, LDMs, are generative models that compress input random variables into a latent space using an autoencoder and characterize this space with a diffusion model, DM. In text-conditioned LDMs, a text encoder transforms a tokenized prompt into a text embedding, which is then used as input for the DM. The DM employs attention modules, including self-attention and cross-attention, to capture relationships within the image embedding and between the image and text embeddings, enhancing the interrelation between text and image. Section 4 Method. We've developed a method called SLiMe, which allows us to segment images at various levels of detail, using just one labeled image as a reference. This method can be applied to both real-world and generated images. The process involves two main phases: training and inference. During the training phase, we first extract a cross-attention map and a weighted accumulated self-attention map. These maps help us fine-tune the text embeddings, which are representations of the segmented regions in the image. Once these embeddings are optimized, we use them during the inference phase to highlight the segmented parts of the image and create a segmentation map. Let's delve into the details of how we optimize the text embeddings. We start with an image and a segmentation mask, which is a representation of the different classes or categories present in the image. We then feed an empty text into the text tokenizer of a system called Stable Diffusion, SD, which gives us a set of tokens. These tokens are then processed through SD's text encoder to derive the text embeddings. We then pass the input image to the encoder to get the image embedding. We add some standard Gaussian noise to the image embedding and feed it, along with the text embeddings, to a system called UNet to get the denoised image embedding. Next, we extract the cross-attention maps corresponding to the first K text tokens. We average these maps across different layers to enhance the results. The final attention map used in our loss function is calculated by averaging the resized cross-attention maps. We then optimize the text embeddings so that the attention map highlights the region of the segmentation mask corresponding to each class. However, Because the sizes of the cross-attention maps are significantly smaller than the input image and the object edges are vague, the resulting segmentation is very inaccurate. To improve the accuracy, we also use the self-attention map, which provides rich information about the semantics of an image and shows the edges in more detail compared to the cross-attention maps. We average the self-attention maps across different layers and resize the cross-attention maps to the size of the self-attention maps. We then calculate the weighted sum of channels of the self-attention map, which refines the edges since the self-attention map has a good understanding of the edges and boundaries of semantic regions. We resize this map and calculate the mean squared error, MSE, loss. Finally, we use the loss function of SD, which is the MSE loss between the added noise and the predicted noise, to prevent the text embeddings from deviating too much from the space understandable by SD. Our objective to optimize the text embeddings is defined as the sum of the cross-entropy loss, the MSE loss, and the SD's loss function, each multiplied by a coefficient. Section summary. The paper introduces SLiMe, a method for performing segmentation at different levels of granularity in both real-world and generated images using only one labeled image as a reference. The method optimizes text embeddings by extracting cross-attention maps and weighted accumulated self-attention maps, which are used to highlight segmented regions and obtain the segmentation map. The optimization process involves cross-entropy loss, self-attention maps, and a loss function to prevent the embeddings from deviating too much. Section 4.2 Inference. In this section, we'll explain how our model works when it's time to analyze a new image, and we'll also share the results of our experiments. First, let's talk about how our model processes new images. We start by taking the image and transforming it into a format that our model can understand. We then add a bit of random noise to this image, the amount of which is determined by a specific parameter we've set. This parameter and the amount of noise we add are consistent with what we used during the training phase. We've included a detailed explanation of why we chose this specific parameter in the appendix. Next, we use the optimized text embeddings and the transformed image to create attention maps. These maps help us understand which parts of the image are most important. We then select the first few attention maps that correspond to the classes we're interested in, resize them to match the size of the original image, and stack them together. Finally, we generate a segmentation mask by identifying the most important class for each pixel. This process can be repeated for multiple images without needing to retrain the model. Now, let's move on to the results of our experiments. We tested our model, which we call SLiMe, on two datasets, Pascal-Part and SLiMe Mask HQ. We ran each experiment 3 times with different starting points and reported the average results and the amount of variation between the runs. For the Pascal-Part dataset, we focused on the car and horse classes, as these were the classes used in the papers we're comparing our results to. We used a metric called MIOU to measure our results, which calculates the overlap between two binary masks. We compared our approach to 2 other methods, Regan and SegGPT, and found that our method performed better on average and for most parts of the images. For the SLiMe Mask HQ dataset, which is used for facial segmentation tasks, we used 2 versions of the dataset that contain different numbers of classes. We compared our method to SegDBPM and found that our method performed better on average. In conclusion, our method outperforms other methods in most cases and is capable of handling complex images with occluded and camouflaged objects. However, there are some cases where other methods perform better, particularly when they are tailored to specific types of images. Despite this, our method offers the advantage of being able to handle a wide range of images without needing to be pre-trained on specific classes. Section summary. During inference, our goal is to segment the test image with the same level of detail as the training image. We achieve this by encoding the test image into the latent space of SD, introducing Gaussian noise, deriving attention maps, selecting relevant maps for each class, resizing them, and generating a segmentation mask. Our method, SLiMe, outperforms Regan and SegGPT in semantic part segmentation on both the Pascal-Part and SLiMe Mask HQ datasets. Section 5.3.1 Occlusion Results. In this section, we'll discuss the versatility of our method, which can be trained on an object that's partially hidden and then used to analyze images where the object is fully visible, or vice versa. This demonstrates our method's ability to understand the semantics of parts and objects. For instance, even if a person is blocking part of the object in the training image, our method can still analyze other images of the same object. This is also true when the training image is of a fully visible object, like a bear, and the test image has some occlusion. This shows how our technique can accurately understand semantics, even when dealing with objects that are partially hidden or fragmented. Next, we compare our method with Regan and SegGPT. Our method, SLiMe, is able to capture finer details, such as intricate hair segmentation, better than Regan. In addition, SLiMe can accurately segment camouflaged animals like crabs and lizards, even when they're hard to spot with the naked eye. SLiMe also has a strong capacity for generalization. For example, after being trained on a single image of a dog with segmented parts, SLiMe can understand the concepts of a dog's head, body, legs, and tail and apply them to test images from various categories. Moreover, when trained on an image containing both a dog and a cow, SLiMe can learn to segment only the dog class in test images. This shows SLiMe's ability to learn either high-level concepts or specific object classes. We also conducted an ablation study on 10 samples of the car class from the Pascal part dataset. We found that the initial text prompt had minimal influence on the results. We also determined the optimal coefficients for our losses, finding that the most suitable coefficient for the semantic distance loss, L_SD, is 0.005. The importance of the mean squared error loss, L_MSE, is also highlighted. In terms of implementation details, we used SD version 2.1 and extracted the cross-attention and self-attention maps from specific layers of UNet. We used an empty string as the input text prompt and set the time step of SD's noise scheduler to 20, avoiding higher values to preserve image structure and detail. We also used Gaussian noise at the start of every training and the same noise in the inference step. For optimization, we used the Atom optimizer with a learning rate of 0.1 and a batch size of 1 for 150 epochs with gradient accumulation of 4 epochs. Our loss functions were calculated by resizing the ground truth mask and our predictions to a size of 128 by 128. We set the coefficients alpha and beta to 1 and 0.005, respectively. For the Pascal part dataset, we followed the procedure of Regan, cropping the object images with the provided bounding boxes, removing images with overlapping bounding boxes, and discarding cropped images smaller than certain sizes for the car and horse classes. For more details, please refer to the appendix.